Hey everyone, I hope I'm live. Let me quickly check once. Yes, I think we're live. Let me quickly check my audio as well. Okay, so we are live. Good evening. Good evening, Pujita. So today we'll be solving the problem, which is a very common interview question, uh, and sometimes actually people get confused around it. Like I also used to get confused around it, like how to solve this. Although the solution is pretty simple and it's not very complicated, right? Like it's just tagged as a medium or a hard problem everywhere, but it's not very complicated thing to solve. So let's understand the problem statement first. So the problem statement is we have to design a LRU cache, right? What is LRU cache? LRU cache, what is cache firstly? Cache is a special type of memory which is actually available with your system. Now caching is a very different very different thing from cache. Cache memory is something that is available within your system, but caching is a very different thing. Although when you store something on your cache memory, it is also called caching, but caching is a widely used term. Like you can have any other form of memory as for caching, but cache memory is a different type of memory, right? So LRU cache is a caching technique. It is not very particular to the cache memory, although the cache memory of your system also follows LRU technique, but it is not particular to your cache memory. LRU cache is a caching technique. So the idea being that generally when you are actually having a system, you have different forms of memory, right? Like you can have a hard disk, HDD, you can have SSD, solid state drives, you can have RAM. There are different forms of memory, right? You can have cache memory, which is faster. So if you look into this, the price actually increases for each of them, right? The price actually increases. Like when you are actually going from a hard disk drive to a SSD, the price is increasing with the increase of speed. The access time for SSD is much lesser than that of HDD. Similarly, the access time of RAM is much lesser than that of SSD. So that's why RAM is much costlier than SSD. Access time of cache is the least, and not the least actually. You have registers after that, which are the fastest, but again, cache is much faster than RAM, but it is much costlier than RAM, right? So the idea is that these memories that you have, right, the cache memory or the RAM, you don't have infinite amount of memory in these, right? But you can have a lot of memory in HDD and SSD and these things, right? SSD also you will maybe have do not have that much what you can have in HDD, sorry, hard disk drive. So you cannot store a lot of data in faster memories. So that's why you need a cache eviction technique, so that you can remove items from the cache as needed and you can replace it with items that you are using frequently, right? So that's basically the technique that is called the cache eviction technique, that you are removing some items that are not being used a lot, and you are replacing that with some items that are being currently used, right? So that you are utilizing the space and you are also getting the speed, desired speed. Because let's say let's say there is an item 10 present in the cache, but 10 is not used, you are using 20 more frequently, so it's better to store 20 in the cache, not 10, right? It is better to store 20 in the cache memory, and 10, it is better to remove 10 from the cache memory if the cache size is full. So this technique is called cache eviction technique. Now there are many cache eviction techniques that are available today. One of them is the LRU technique. LRU means least recently used. Whatever the name suggests, it does basically that. Whichever thing in the cache memory is the least recently used, it will remove that. So that is the cache eviction technique. So you have to design a data structure that works like a LRU cache. So you have to design LRU cache. Here cap denotes the capacity of the cache and Q denotes the number of queries. So cap basically means This is the maximum capacity of the cache that you can have. As I said, the cache memory will be smaller than other forms of memory, right? So there is a limit to the cache memory that you have. You cannot store everything in the cache memory or in the caching memories that you are using for caching. So you have to remove some items and you have to replace them with some items, and that is called cache eviction technique. And LRU is one of the cache eviction techniques. So you have few queries. Queries can be of two types: set x y, where it sets the value of x to y, and get x, it gets the key of x and returns -1 otherwise. The LRU cache class has two methods, get and set. Okay, get key, it returns the value of the key if it already exists in the cache, otherwise it returns -1. Set key value, if the key is already present, update its value. If not present, add the key value pair to the cache. If the cache reaches its capacity, it should invalidate the least recently used item before inserting the new item. In the constructor, you are given the capacity of the cache. So this is the question, right? Let's look into some examples. Is the question clear with everyone? Is the question clear with everyone? Let me know in the chat if it is clear with you, and if you want me to repeat anything, just let me know. Okay, so you have, let's write down the things here. Okay, so you have capacity of 2, you have a capacity of 2 for your cache. So your cache can store 2 items. Basically it can store 2 items. So I still have my internet. Okay, I think I'm having internet. I'm still having internet. The power went out, so that's why I was wondering if I have internet. Please repeat. Sure. So the question is basically, so you are clear about cache memory, right? Caching is basically storing the data in a faster memory so that you can use it. Like if a data is being frequently used, right? Let's say there are some student records. Let's take an example to understand cache memory. So there are some student records, right? Let's say student 1, student 2, there are multiple student records, and corresponding to student 1 there is a lot of data that is there. Student 3, the data is there. Student 4, like this. Now let's say you are building a website where where you will be displaying the data of the for a student for which it is being queried. Now you see that student 1 is not at all querying, right? Student 1 is not at all querying. Let's say he's asleep right now, but student 2 is refreshing the page again and again, right? He's querying multiple times, he's waiting for his result multiple times. Let's say he has got 100 and his parents are not believing that, right? So he's just refreshing the page and trying to show them as well, or connecting from various devices. So you have a lot of queries that are from student 2. You have some cache memory where you can cache the student data, right? So let's say student 1's record was cached. Isn't it better, as student 2's record is being frequently asked for, isn't it better to cache student 2's record and remove student 1's record from the cache, because it is not being used at all, it is just unnecessarily occupying the cache memory. So this technique of removing what is not needed within the cache memory and inserting something that will be needed, that we are predicting that might be needed a lot in the subsequent requests, this is called cache eviction technique. So we are removing something that is called cache eviction technique. One of the techniques is the LRU technique, which is called the least recently used technique. That means whichever item is the least recently used, it is not used for a long time, remove that, right? Whenever the cache size is full, just remove the item which is least recently used. So if you see the three type of queries that we have a get key, where we'll get the corresponding data for a given key. We have a set key value. If the key is if the data is present, update its value. If the data is not present, you have to add that data to your cache memory. Now in your cache memory, you might have your cache size full, right? You have a capacity given to the cache. You cannot have more than let's say the capacity is 2. You cannot have more than 2 items. So you have to remove some items to accommodate this item. So what item will you remove? You will remove the least recently used item. So that's the LRU cache policy. Okay, and in the constructor you are given the capacity. So let's quickly take an example here. So we have 2 and queries are 2. Q2, I think, okay, cache size is 2, set 1, I think it is okay. Let's take a better example. Okay, you have query, the cache size is 2, and there are given 8 queries are given to you. The first is set 1 2, then set 2 3, then set 1 5, then set 4 5, set 6 7, get 4, get 1, set 1 2, get 3, like that. Okay, so let's actually understand this. So first query is set 1 2. First query is set 1 2, so we can actually take like this. Okay, set 1 2, what we'll do is we'll set 1 2, will add it to the cache. The cache size is 2, right? So 1 is added to the cache and the value of 1 is 2. 1 is added to the cache and the value of 1 is 2. Okay, now set 2 3, set 2 3. So 2 is added to the cache and the value of 2 is set to 3. Now set 1 5, set 1 5. Okay, 1 is already there in the cache. We'll just update the value of this 2 to 5. Okay, set 4 5, set 4 5. Now this is interesting. We are setting 4 with the value of 5, right? We are setting 4 with the value of 5, but our cache is full. So which is the item that will be removed? Which is the least recently used item? If you see, set 1 5 is called just before this, so 1 is the most recently used, 2 becomes the least recently used, so 2 will be removed from the cache and 4 5 is set. 4 5 is set. Okay, after that set 6 7. Now which is the least recently used item? 1 is the least recently used right now, so 1 will be removed and we'll set 6 7. 6 and the value of 6 is 7. Okay, after that we have get 4. Get 4, 4 is there in the cache, so we'll return 5. After that we have set 1 2. We have set 1 2. Now 4 is recently used, right? We had a get 4 recently, so 4 becomes recently used, so 6 will be removed from the cache and we'll return, we'll set 1 2, so we'll add 1 to the cache and the value of 1 will become 2. Now we have get 3. Get 3 will return -1, so the output is 5 -1 because it is not there in the cache, right? It is not there in the cache. So this is what we have to implement. I think the question is clear with everyone. Let me know if the question is not clear. Let me know if the question is not clear with anyone. Is the question clear with everyone what we are doing exactly? Okay, great. So we have this question now, how to solve this? First thing to note, let's say we just obviously we are storing some key value type data, right? So it's very obvious that we would need something like a map or a hash map kind of thing, right? We'll need something like a key value data store where we can get, given the key, we can get the corresponding value out, right? So it's very obvious that we'll need a this type of store. But the problem here is that we also have to remove some items. So how do we prioritize removing the items? And not only that, the main part being that, let's say we have a cache size of 3. So let's say 1 is called, after that 2 is called, after that 3 is called, right? Now again 2 might be called, so the priority of 2 will change, right? The priority of 2 will change. So we have 1 2 3. Let's say these are their priorities. 1 is called, 1 has a priority of 1, that is it is most frequently called. 2 has a priority of 2, 3 has a priority of 3. Now 2 is called again, so the priority of 2 is actually changing to 1. And not only that, you have to adjust the other priorities. You have to make these two, one's priority becomes 2, 3's priority remains 3. Now let's say 3 is called, so 3's priority is changed to 1, 3's priority is changed to 1, 2's priority is changed to 2, and once priority is changed to 3. Now if you have to remove an item, if let's say you are inserting 4, which one will you remove? The one with the least priority, right? One is the maximum priority, let's say, or the most frequent, like the least frequently used. You priority here means 1 means more priority, 3 means less priority, right? So we'll remove this item, right? We'll remove this item. Okay, so what we need is, we also want to have this arrangement dynamically, like everything will get updated automatically when one of the items priority is increased. Everything will be adjusted automatically. What can we do here? So we have a data structure with us, in which we can flexibly move around items. Can anyone tell such a data structure in which we can flexibly move around items? You have an item here, you can flexibly move it anywhere else. Can anyone name such a data structure where you can flexibly move around items and other items are arranged based on that automatically? Is there a data structure with us where we can flexibly move around items? Because that's what we want, right? We want to flexibly move around the item. Like, let's say we are storing the priority in an array, in a queue, let's say in a kind of a queue. So let's say 1 2 3 is currently, like 1 has the maximum priority. Now suddenly 2 is called, so 2 will have the maximum priority, so it will be automatically adjusted like this, 2 1. Now let's say 3 is called, it will automatically be adjusted like this, 3 2 1. 3 will have the maximum priority, right? So do we have a data? Yes, exactly. We have a linked list like data structure, right? We have a linked list where we can actually adjust these things quickly. And more specifically we'll need a doubly linked list, but that's later on, because doubly linked list definitely gives us more flexibility, right? So linked list is a kind of data structure that gives us this flexibility, right? So what we can do is, we can maintain this priority in a linked list. So we have one, let's say we are assigning the we are keeping the things like this, 1 2 3, right? Now we have to increase the priority of, let's say 2 is called, right? So we have to increase the priority of 2. What we can do is, we can just remove 2 from here. We can just attach 1 and 3, and we can bring 2 at the front. So with this only, if you see, now the priorities have changed. 2 has first priority, 1 has second, 3 has third priority. Now let's say 3 is called, so 3 can be removed from here, and we can bring 3 to the front. So basically we have to bring an item to the front whenever whenever it is being called, right? So this is how we have to do, this is how we can do. But again, there is a problem with this. The problem is that if I am given 3, first thing is, how do I know I have it in my cache? One way of knowing is, we are already maintaining this map, right? Map of key value. So we can mark it to be -1 if it is removed from the cache. Second way can be, second way we'll not think about that. Let's focus on that only. Second problem is that when you are calling something, right? When you are calling an item, how do you know where is that item present in the linked list? You would call set 3 or get 3, right? You would not call with the node. So where is this present in this linked list? We don't know. And if you have to travel the entire linked list, it will be order of capacity per query, right? Means you have to travel this entire linked list every time. So it's order of capacity per query. So we have to have a better way. So that if we are asked for any set or get operation, if that is in the cache, we can quickly return what is the corresponding node against this, where is this present in the memory, or what is the corresponding node. We should have a node pointing to that somehow, that we can quickly get this node. Given 3, we can quickly get the node to 3, that is 3 is here. Or given 1, we can quickly get the node to 1, that is 1 is here. We can quickly get this. If we are able to get that, and we have a doubly linked list, we can easily move around, right? So that's basically the idea. How do we quickly have this node? How can we have this node quickly? We can maintain another map, where map of key will store the pointer or the reference to that item. Pointer in cache. It will store the pointer in the cache memory. Like, where is this key present in the cache memory? What is the preference of this? So it will store the pointer to this. Now we'll move the pointer only around, right? We'll just move the pointer around. Actual memory location remains the same. So let's say 3 is there in memory location 2000. So we'll just store map of 3 with the value of 2000. Now 2000 can be the next of 2000 can be the head of the linked list, or we can have, let's say, 1 is reference, so 2000 can be the second item. The memory location is not changing, right? Only the relative order is changing. The memory location is not changing. This is fixed, so we can store this value in the map. So that's how we can do. So we have actually optimized everything. Is this clear? How have we come to this part? Is this clear with everyone? Let me know if this is clear with everyone, or anyone has any doubts with this, like any part what we have used. Anyone has any doubt? Why are we using a linked list? Because of the priority, because we have the flexibility in a linked list to move around. Why are we using, and also they will automatically, all the other items will automatically get ordered when one of the items is moved at the front. Second is, why do we need a map along with the pointer to the node? Because we need to quickly access the place where it is located so that we can quickly move around that. Otherwise we have to travel the entire cache. So that's something that we don't want. So that's why we are using so many things. Let's quickly write the code for this. I was actually thinking about implementing the linked list myself. I am not sure how to have a HTL for linked list. I never used that, but yeah, I can definitely implement a linked list myself. So type def, let's what can we do? Yes, we can have a class. We can definitely have a structure. Type def struct linked list, and we'll have a doubly linked list, right? Doubly linked list. Let's call it DLL, or we can call it DLL like this, and DLL. Okay, so what will it contain? It will contain, we are making two maps. Yes, one map will be needed for the key value pair. Like, what is the value for that? If not a map, then an array. I'm not sure about the constraints here. But yeah, we have to have two maps. And also, again, everything should be order of one. How will it be? If we just have a unordered map, like, it will become order of one, right? So we just have to search in the map, where is that node? We have to get that node, we have to move that node to the front of the linked list. That is also order of one operation. So everything is actually order of one, right? So struct DLL, here what will contain is in data. Okay, so we'll have int value, the value of this, what is the data that is present here, and also what is the DLL star next and previous. DLL star next and DLL star previous. Okay, and yes, we can have a constructor here, DLL, default constructor, which will be val equals to 0, next equals to previous equals to null. And we can also have a constructor like this, int v DLL star n DLL star p, copy constructor, not a copy constructor, parameterized constructor, where we'll have val equals to v, next equals to n, div equals to p. So we have this, and now we can quickly implement all the methods for a linked list. So DLL methods, let's call it DLL methods, or we can call it the cache as well. Or what we can do is, what do we want actually? We want to remove, I don't think we need any methods for now. Let's just focus here only. So we'll create in the private section, we'll create the cache. So it will be a DLL start. So DLL star cache memory, right? And capacity will maintain here as an integer in C capacity. So wherever whenever it is given, so we'll have C equals to capacity. That will be the only thing that we will do. Now get key is, we'll implement this later, first of all. Or get key also, we need two more things, right? One will be unordered map int what will be the key value pair. So what will be that? That will be basically data store. Let's call it a data store, where the data is stored. and unordered map. Second will be int and DLL star. It will store a pointer, right? It will store the pointer. So DLL star, it will be what? It will be cache location. Let's call it cache location, right? So we'll store these two things. So firstly, we have to clear these two things. So data store dot clear and cache location dot clear, right? So now what we can do is get key. So we can just search it in one of these maps. If data store dot find key not equals to data store dot end, right? Data store dot end, we can just return data store. We can just return data store of key, whatever is the value, and otherwise we can return -1. It is not found, so we can return that. Here we'll create a few helper methods. Helper also will need a few more things. Actually, this is kind of the cache head. We'll call it the cache head. We'll also need the cache tail as well. So cache tail. So we'll need that, and we will create a few methods. First is insert at front, right? We'll always insert at the front. We will always insert an element in the front. So void insert at front, because it will have the maximum priority. We'll remove from the end, insert at the front always. So insert at front, and we'll pass a value here, val. We'll insert that at the front. So we'll insert that at the front, and actually we'll pass a node directly here. Let's pass a node directly here. So DLL star node, will insert this into the front. So node of next will be equals to cache head, and cache head equals to node. And if cache tail equals to null, in that case cache tail will also be the node. So cache tail is also equals to node. So that will be the insert at front. We'll write remove at end. So void remove at end in the cache. So we are removing the item at the end. So what we'll do, that's the tail, right? That's the tail. So first thing we'll check if tail equals to cache tail. I'll not check for null, because I don't think we'll ever call this when the cache is empty. So I'm assuming that we'll never call this. So cache tail, otherwise we can definitely add a condition, but let's assume that it will always be have some item. So cache tail equals to cache head, then we can make both of them null. So cache tail equals to cache head equals to null. Otherwise what we can do is DLL start temp equals to cache tail. DLL start temp equals to cache tail, the previous element of the cache tail. So cache tail previous, cache tail. And also one more thing that we'll do, yes, let's do that first. Cache tail equals to cache tail previous. Cache tail the previous will go to the previous item. And what else we'll do, we'll remove it, right? So we'll remove it as in delete temp. But before we delete temp, we also will do one thing. We'll remove it from the data store as well. So data store dot remove, erase, data store dot erase temp of val, whatever if it is there in the data store, it will remove temp of val, and also will remove it from the cache location as well. Cache location dot erase temp of val, and after that we'll delete the free the memory. So delete temp. So these two I think will help definitely. And next, what will be there? give priority to an element that is already present, right? So we have to give priority to an element that is already present. One more thing that we can do here is we can actually add these things here, right? We can actually add these things. So we can data store, I'm assuming that it is already populated in data store, but we can definitely add here cache location. So cache location for node of val, cache location for node of val will be equals to the node that I'm at right now. So or it's basically same as the cache hit, right? So it will be the node that I'm at right now. Okay. What else? Will also create a method that will prioritize something, right? So prioritize, and it will be prioritizing a given node. So dll star node, a node will be given to us, we will be prioritizing this. So if node equals to cache head, if that is there, so we'll just return, will not we don't have to do anything, it already has the first priority. Other than that, if it is not that, so what we'll do is node of previous of next is equals to node of next. We'll first assign, we'll first break the link next, and also node of next of previous, we have to break this link as well. Node of next of previous, actually we haven't broken a lot of links actually. We have to do that. Node of next of previous will be equals to node of previous, and then we are moving node to the front, so node of next will be cache head. Cache head of previous, cache head of previous will be equals to, cache head of previous will be equals to what? It will be equals to node, and cache head equals to node. Okay, cache head equals to node. Actually implementation, I'm implementing everything myself actually, but if definitely you can use the data doubly linked list if it is available in C++. I'm not sure if it is. I have never used I have never created a doubly linked list myself. Sorry, I used the HTL for double linked list, I always create them myself. So node of next is trash it. I think here I have made some mistake at insert at front. We haven't actually done a lot of things. One thing that we have not done is cache head. Node of need is cache head. So if cache head is not null, so if cache head not equals to null, in that case cache head of previous will be equals to node. This is something that we have to do. And this is, we are deleting the item, so it's okay. I think we don't have to do anything at the remove at end. Cache head equals to cache tail equals to null, that's fine. I think that should be that should be enough, like we should be good to go here. Let's see, is there anything? Cache head equals to node, we are just changing the priority, so we are not actually changing the, is a node previous next, node of previous, no, node of previous, and node of previous is next, we are assigning a new value. So we are going to node of previous, and to its next we are assigning the new value node of next. So yes, node of next of previous means the same, like we'll come to the same value, but we are actually assigning here. This is an assignment operation, right? So we are actually going to the node of previous, and node of previous, whatever it is, its next we are assigning the value of node dot next. So what we are basically doing here is, let's say we have something like this. Here the canvas. Okay, so let's say we have something like this, that let's say I have one like this, I have two, I have three like this, right? So what is this? Is node, right? Node of previous is 1, once next will be node of next, that is 3. So this link is broken, this link is broken, once next is becoming 3. Similarly, node of next of previous, that is node of next is 3, its previous becomes equals to node of previous. So this link is broken and they point to each other. So basically this is gone from the between, right? Something like that. I'm not sure if there might be some small mistakes that I've done. We'll figure that out later, but yeah, like that's the idea actually here. Okay, I think we are done with most of the things here. So let's see, this is okay, this is definitely, this will work. this will work, but now set will be interesting actually. So first thing is, if it is a new element, right? If it is a new element, data store dot find key equals to data store dot end. So let's go to full screen mode actually now. Okay, data store dot end. So it means it is a new element, right? So it is a new element. So what will we do? For the new element, will be definitely first stored in the data store. So data store of key equals to value. We'll add that. After that, what we'll do, we'll also do one thing here. So that is cache location. We are already populating cache location here. So insert at front. We'll just do insert at front, right? Insert at front. And what we'll do here, we have to have a new node here. We have to have a new node created here. So let's create a new node here. So new, I think we can create a new node here. So DLL star node equals to new DLL, and we can pass the parameters here. So first of all, the value will be, we only know the value, so the value will be this. Remaining everything will pass to be null. We'll pass everything to be null, and we'll pass this node here, insert at front. So at the front, and also we have to do a few things here as well. So I think insert at front is okay, but when we prioritize cache of, okay, cache head of previous will be equals to node, cache head equals to node, node of previous of node of next is cache head, node of previous is null. That is something that we haven't done yet. So node of previous is equals to null, and cache head of previous equals to node, cache head of previous, yes, and cache head equals to node. I think that should be good. So yeah, we have done this. Node equals to, and if it is equals to cache head, then so that's totally fine. If it is not equals to cache head, then we have to do something. Also here we can check here node of previous of next, node of next of previous, right? So if node of next of previous is node of next is null, that is node equals to cache tell. So if node equals to cache tell, also we haven't adjusted our cache tell here. So if node equals to cache tell and else, so else if node equals to cache tell, so cache tell will be what? Cache tell will be equals to node of previous. Cache tell will be equals to node of previous, right? And node of next, otherwise if it is not equals to cache tell, then node of next of previous will be equals to node of previous, and node of next is this cache is node. Okay, that is done. And cache tell also we have done insert at front, so it should not be a problem. Cache tell is cache tell dot previous. I think that should be fine. So data store insert at front node, so it is inserted at the front. Else it is there, so else it is there. So one more thing that we have to maintain, I think, although we can definitely maintain here itself, like we can definitely maintain see from the cache data cache location or data storage as well, or we can do that as well, right? So let's do that only. Like what is the current capacity of the cache? So else it is okay, before we are entering a new element, actually we are entering a new element, right? So we have to check here, so what we have to check, if before we insert this new element, so we have to check here, we will check if data storage dot size, if it is already equals to C, then what we have to do is we have to remove the last element, right? So remove at end. So we'll have to remove the last element, remove at end. We have to call this remove at end, and it actually removes from data store as well as cache location, so it's fine with us. So that's there. Okay, now if it is present already in the cache, in that case what we'll do, we'll just set the value. So data store of key equals to value, and we will just prioritize. Let's call it prioritize method. We have a prioritize method, right? So it will prioritize a given node. Where is the node stored? Node is stored in the cache location, right? So node is stored in cache location, so cache location, and for the given key we'll just prioritize that. We'll just prioritize that. So yeah, I think that should be the code. New element, and this is existing element. We are prioritizing that. And also here also we have to prioritize. So here also we have to prioritize and it will be cache location and it will be key. We'll prioritize that and return data store of key. So this should be the code. Let's see if this works. Okay, there is some segmentation fault. Let's quickly see what we might have done wrong. So DLL next previous, everything is set to null. Everything is set to null, and we are initializing. We have a we have a parameterized constructor here that also works, I think. Yeah, unordered map, data store, and this. Okay. Initially we have c equals to capacity. We are setting that value and we are clearing everything up. Now data store dot find key not equals to, will prioritize. Let's talk about prioritize a bit. So node equals to cache node. If the given node is equals to the cache head itself, there's nothing to prioritize actually, so we'll just return. Otherwise node of previous of next will be equals to node of next. So node of previous, it is not equals to cache head, so definitely it has a previous node. So node of previous, its next will be equals to node of next, and node equals to cache tail. If it is the tail node, in that case cache tail will be node of previous, and node equal, otherwise node of, it is not cache tail, so definitely there is node on the right as well. So node of next of previous equals to node of previous. So you're connecting that to those two things, next and previous. I think that should work. And node of next equals to cache head. It was moved at the front. Its next will be cache head. Node equals node of previous equals to null. Cache head equals to cache head of previous is equals to node. That will be node, and cache head equals to node. So you have prioritized, we have prioritized successfully. So prioritize should work fine. Okay, prioritize should work fine. After that, what do we have? We have set first is we have a new element. So if we are seeing if it is equals to c, then we are calling remove at end. So remove at end, what it does, it will remove an element from the last of the linked list. So if cache tail equals to cache head, that is there is only one node. Node of previous of next equals to node of previous of next, node of previous of next of next, node of previous of next of next. We haven't done node of, we have done node of previous of next, right? So node of previous of next, this should work. I believe this should work. Like this should work. Otherwise we have to extract in a different variable, but again, like this should work actually. Not sure, but this should work. We'll see, like if that is the reason. I think there should be some other reason it's failing. So cache tail equals to cache head. Cache tail is equals to cache head equals to null. DLL temp is cached. If it is empty, basically we are setting both of them to null. Otherwise temp is equals to cache tail. Also we haven't removed deleted the node. So DLL start temp equals to, oh okay, so equals to cache tail and delete temp null and return. We have to return as well. Otherwise or also before we return, we have to do these things as well. Okay, we have to do these things as well, and this might come front. That's fine. Will come front, and cache head equals to cache tail equals to null. Will remove from the location. Other than that, anything else? Cache tail is cache tail of previous. Also cache tail is cache tail of previous. Also cache tail of next will be equals to null. Cache tail of next will be equals to null because it will be deleted now. So cache tail equals to cache tail of previous. Data store dot erase temp dot val delete temp. Okay, this should work now. Finally we have insert at front. When we insert at front, node start next equals to cache head. Node next equals to cache head, it is inserted at the front, so its next will become cache head. Yes. Cache head not equals to null, then cache head of previous will be equals to node. We are establishing that connection. cache head. Okay, so cache head equals to node. If cache tail equals to null, then cache tail is also equals to node, and cache location is cache location node of val equals to node. So that is also what we are doing, so that should be fine. Okay, I think was that remove that end only issue, not sure, let's see. What's tomorrow's lecture? Tomorrow we'll be discussing about the largest area under histogram. Okay, it is taking a lot of time to run, I'm just afraid. It's segmentation fault, still segmentation fault. Where is it getting a segmentation fault? I think set 1 2 is not even executing. So set 1 2 will basically call, it is a new element. So the size is definitely not equals to c. We are inserting that as well, right? So I think it should be okay. This part, data stored of key equals to value, here we are inserting. Okay, data stored of key equals to value, node equals to new dll, and insert at front. And insert at front, are we doing some mistake at insert at front? So node of next is equals to cache head. We are making it point to the cache head. If cache head not equals to null, cache head of previous equals to node. The previous of cache head will become node, that's true. And cache head will be equals to, node of next is cache head, it's set. Node of previous is already null, we don't have to do anything there. And cache head of previous becomes cache head equals to node. If cache tail becomes node, cache location node of val equals to node. Okay, we are also giving node here as well, so it should get the proper pointer. It should get the proper pointer. I don't think there should be a problem here. Okay. Remove at end should not be called, right? In the first case, remove at end is never called. In this case, we have set 1 2, we have cache size of 2, right? And we have just one set operation, so remove at head is never called. And we can actually verify that as well. How we can verify? We can actually add a statement here. See out everything, like we'll just insert, do some see out insert at front is called slash n. Let's do a see out here as well. Remove at end is called, and slash n. And see out prioritize is called, so see out prioritize is called and slash n. So we have these three outs. We have these three outs. Let's see what is called. So we'll try running this. Okay, I don't have any output. That's pretty nice. Where do we come? First that is called, right? See out hello world. Or do we not get output? Do we not get output if it is segmentation fault? We're not getting any output. That's interesting. So when it is calling LRU cache, is it failing here only? Let's see out inside constructor slash n. Okay, it doesn't give any output. Interesting. Not sure why is it not giving any output to us, but inside constructor it is accessing something that is null. Okay, I think I've got it. DLL cache head. So we have never made this cache head, right? So we have to make this cache head equals to null. and cache tail equals to null. We never do this. That's true. That's why our condition checks will never be true, to be honest. But still it's not working, so definitely that was one of the issues. Cache head, cache tail, c equals to c we are assigning. We are clearing both of them. Cache head equals to cache tail equals to null. So here if it is null, here it will definitely like be it will satisfy these conditions. So inside constructor slash n, c equals to cap capacity data store dot clear cache location dot clear cache head equals to let's do one thing. Let's just return anything from here. Return -1, and we'll here also we'll just return. We'll not even execute this. So just to pinpoint out like which part is failing. Okay, inside constructor now we are getting, so inside constructor it's coming. So this is executed correctly, and after that we have -1, so which is okay. Here it is returned directly. So let's see what we can do. So let's try to see if it is going. So let's remove this. So data store dot find key equals to data store dot end. So let's okay, else data store of key equals to value. Cool. So if it is a new element, let's see, let's paste it here, return, and it should not go to remove at end. It basically should complete, and it should never go to remove at end. Just it's not going to remove at end. That's fine, that's expected, right? And insert at front, here we'll do add a return statement, and here it should break basically. Okay, insert at front is called, and it is not filling at insert at front. That's nice. It's not filling at insert at front definitely. So this is called, and it is not filling here. Okay, after that what is there? So after that something is happening. Return, and it is coming here, right? So it is coming here, and somehow here it is filling. If I run this now, it should work basically. This entire thing should work. Okay, yes, this set is working till now. Here we have some problem in prioritize then. Got it. So we have some prioritize problem. So most probably it's coming data store dot find not equals to end. It's coming to this prioritize cache location key. Cache location key, it is calling prioritize, and here we are having some problem. So let's return return from here. So let's return from here. Prioritize is called. So this is getting called. Node equals to cache head return. Node is the cache head. What is called actually? Get is called one. So it node is equals to cache head only, right? Can we do something like this? I think there is some issue with this part. Okay, that's interesting. Plus node of val, and then slash n. Okay, the node of val, whatever is the value of the node, will print that, and slash n. Let's see if it gives something to us. Okay, I think the node it is receiving here, I think the node cache location of key, it is actually not giving it anything. So our insert at front, it should have given the cache location of node. It should have got a new node here, node of val equals to node, and let's add a cout statement here. Cout cache location of node of val, whatever it is of val, and slash n. Let's see out this as well here. We'll verify here if it is actually setting the value. So prioritize is called, and we will just add a return statement for now here. Let's see what I think. Cache location has some problem. Okay, we have two, right? We have two. The value is two, which is okay. It should be two, right? It should. Okay, 1 second. No, 1 second. No, no, no. Hmm. I think we have done a mistake here. So yes, silly mistake, but it was a mistake indeed. So we were when we were creating that linked list node, we used the value instead of the key. It should have been one here, right? Now, if you run this, you will see what is happening here. My bad. So here, if you see one, it should be one, right? It should contain the key, not the value. So although the name is kind of value, but but it should actually contain the key in the linked list, not the value. So remove at end, and let's remove everything. Prioritize, let's remove, and yeah, I think everything else is removed, so we are safe to execute. Let's see. Okay, our output is 1 2. Where are we printing? 1, yes, here. So let's remove this as well, and let's run this now. Okay, so we have 2 and expected is 2. Let's try to submit. Or we could have actually tested across custom cases as well. I think it will work. Yes, it has worked. So this is how we can solve this. Yeah, it took some time, but a small mistake. What can be done about that? Yeah, so this is how you can solve this. Any doubts that you have with the code? Anyone has any doubts with the code? Any doubts with the code anyone has? Otherwise, we can end the stream here. Did you understand how we are solving this? Like, it's pretty simple actually. You just have to understand what is required, right? So whenever you are getting a problem, the first thing that you have to identify is what is the data structure to use, and to identify that, you have to identify what you have to do, right? With the data structure, we saw that here we had to move items freely, and automatically the priority of other items would change. So we know that there is only one way to do that. If we have a linked list, we can move things to the front, and automatically everything will be arranging itself. So that's why yes, most of the functions, but if you see, most of the functions are removing from inserting in the linked list, inserting in a double linked list, removing from the end in a double linked list, and prioritizing, that is moving an element to the front, moving a node to the front of the double linked list. So these are the methods, right? Any doubt, anyone else, anything that you didn't understand with the logic? I'll definitely recommend you to try it on your own, because this is a very good problem. So do try it on your own. But if you have any doubts here, let me know. Let me know if you have any doubts. Is it clear with everyone? Try karna khud se. You guys should definitely try it out. And yeah, so tomorrow we'll be solving on the largest area under histogram problem, and that's the prerequisite for that will be yesterday's stream, where we discussed about the various variations of next greater element. So we'll be using that to compute the largest area of a histogram, and that is also okay. What is in private? So private I have made because I don't want these methods to be available, right? I don't want these methods to be available. These are needed within my class. So private, this is just a better design that I've done. Like, you can definitely write the methods in the public section, but I don't want these methods to be available outside. These are for internal use to prioritize. So what is the use case of prioritize? It is basically moving a node in double linked list to front. So this is basically prioritize, moving a node to the front of the double linked list. Remove at end, remove a node from end at in double linked list. So you have to remove a node from the end in the double linked list, and insert at front. It is also pretty simple. Insert a node at the front. Insert a node at front of doubly linked list, right? So this is the function of each of the methods, nothing else. These are all double linked list methods. Insert at front, remove from end, and prioritize, like moving a node to the front of the doubly linked list, nothing else. So these I've kept in private section because they are private to my class. I don't want them to be used by outside. I just want these to be used by the methods that I have here. These methods will be using those to compute, like to properly compute everything. So is this clear with everyone? Is this clear? If you want, I actually can arrange a class where I'll be basically discussing all the methods on a linked list. Like what are the various methods that you can have in any linked list. We can actually do that as well one day, where we discuss all the methods that are possible in a linked list and we'll try to write the code for each of them. So I think that will make things much clearer. But these are only linked list methods, like moving a node in a linked list in and out, nothing else. Okay, okay, we'll do that then. We'll definitely do that in a class. So yep, thank you guys for joining. I think you have learned something new. So do make sure to try this out. Definitely try this out by yourself once. And yes, I've taken that a note. I'll definitely create a class. I'll take a class where I discuss all possible methods of a linked list. I'm pretty sure that if most of you would understand the methods, but again, writing the code might be a bit challenging. So we'll try to write all the codes. So yeah, thank you, and we'll see you in the next class.